All right, so welcome back. We're in our third and final part of our Module 10, talking all about the universe here today. So here are your readings again. Make sure you guys are doing that. Just a reminder, I'm going to go through this really briefly. Module 10 quiz is due Tuesday, April 21st. Make sure you watch the planetarium video that I provided the link for. And then also make sure you're working on your PowerPoint presentations. If you have any questions, please send me an email. There's not like a sheet of paper that says exactly how to do it. All I provided is the basic concept, as long as you've selected your topic, and then also the grading rubric. So feel free to get creative with these presentations. I tried not to limit any sort of creativity or way that you want to do your presentation, as long as you're following the rubric and doing what is being graded on. So make sure you're doing your works cited section, making sure you're presenting it clear and concisely, and then also make sure your PowerPoint presentation itself looks very nice. So make sure you're doing those. I'm excited to see how everybody's presentation turned out. And if you have issues with figuring out how to get me your recording or how to present it to me, reach out. I've provided 5 or so options, and I'd be happy to chat with you more on different options on what you can do to get that turned in. Okay, so today we're talking about the origin of the universe. And so we pretty much went through and talked about the 7 sections for our reading, all the way from starting with the night sky through galaxies. But now we're going to talk about the origin of the universe, and we did touch on that a little bit when we talked about galaxies for the last presentation that I uploaded. But so some of it is going to be review, but we're going to cover some new topics as well today. We're going to be talking about the Doppler effect, redshift, and some other concepts as well. Okay, so if you recall from our part 2 of Module 10, we started talking about the Big Bang and how that initially formed our universe. One important thing to remember about the Big Bang is that it is not a steady state universe. So that means it's always changing, it's not steady. And in our case, the universe is expanding outwards here. And if you recall, we also talked about the cosmic background radiation that's present after the Big Bang occurred. And you can see here in this image itself, the afterglow of the Big Bang here is present. So if you remember, we did talk about the universe being approximately 13.7 billion years old. And this was based partially, if you remember, on Hubble's law. And so with all of the research and the study that Hubble did, looking at different galaxies, or over 600 plus galaxies, he determined that slower galaxies are closer to us. And your book uses a really nice example of bread and raisins. So if you were making raisin bread, and you mixed the dough up and you added the raisins to it, and you have the ball of dough where the raisins are all very close. If you put that bread in the oven and start baking it, that bread is going to, or that dough is going to become bread. And in order to do that, it needs to rise and expand outwards. And so the raisins in this example here are galaxies, or so you could even consider them as stars in the galaxies. But as time goes on and you're baking this bread, the galaxies are moving farther away from a starting point. And so that's kind of very similar to the research that Hubble determined in all of his studies. So you can also think of Hubble's law in two different ways here as well. So all of the galaxies here are flying apart from each other, and then also the space between the galaxies are expanding. So, and the bread does a really good visual for you in determining these two ways you could think of Hubble's law. And then also here in purple, you can say pretty much that there's, using the bread example or using real life example, there's really no special place in the universe. So it's hard to ask where is it expanding from. So you can't really ask that. And then also all observers are seeing the same thing. So I've included a video here, and during all of the PowerPoint creating that I had been doing the past couple days, I was asking myself a lot of questions that maybe you might ask in class. And so one good question that I thought of that is probably really relevant to you guys is, so we know the universe is 13.7 billion years old, right? So how can we determine that the universe is 92 billion light years wide? Well, that's way more than how old the universe actually is, or how can stars burn for billions and billions of years? Well, I found a video that's about 9 minutes long that he does a really good job of explaining it. So hopefully bear with me here. I watched it and I thought this video was really interesting, so I'm going to play it for you guys, and it is 9 minutes long, and if you want to fast forward this is fine, but I thought this was really relevant, and I'll be here for the next 9 minutes or so watching this with you. So I'm going to go ahead and hit play, and we can stop it a little bit early and don't have to watch it all the way to the end. But okay, so this is a really good video answering this question.
When we look out into space, we are not only looking at things that are far away, we're looking at things that existed in the past. For instance, the sun is about 93 million miles away, and it takes light about 8 minutes to get here. Thus, when we sit down in the morning with some toast and our first cup of coffee for the day and look at the sun, we're seeing it not as it is now, but as it was when we put the bread in the toaster. Time and space are inextricably intertwined when we talk about how far away things are. This is especially true when we talk about large-scale structures of the universe. We even have a distance scale called a light year, which is the distance that light travels in a year. In more familiar terms, a light year is 9.5 trillion kilometers, or just shy of 6 trillion miles. We use the unit light year because nothing travels faster than light. It's very convenient. But it is most convenient when we talk about the size of the universe. Astronomers have determined the age of the universe very precisely. It is 13.7 billion years old. Exactly how we know this is perhaps the subject of another video, but for the moment, let's take that number as a given. If we do, we can ask a very simple question. How big is the visible universe? There are lots of tricky ways to think about that, but let's start with perhaps the most obvious. We can't see the universe before it began because, well, that's what beginning means. When the universe began, it was filled with light, which then traveled through the cosmos. And if the universe began 13.7 billion years ago, and we're just now seeing it arrive, it had to have traveled 13.7 billion light years before it hit Earth. And to make that point solid, astronomers can actually see light from shortly after the universe began. It's called the cosmic microwave background radiation, and it is the oldest thing we've ever seen. It is hitting the Earth from every direction, and it is, to all intents and purposes, a photograph of the birth of the universe 13.7 billion years ago. Accordingly, it would be reasonable to say that the visible universe consists of a sphere centered on the Earth with a radius of 13.7 billion light years. Boom, done. Except that this is completely wrong. That's one of the sneaky things about science. It can fool you if you think too fast. sometimes you have to slow down and mull things over. And if you think about it for a moment, you'll realize that this way of thinking assumes that the universe is static, and, at least on average, distances between objects aren't changing. But we know this isn't true. To begin with, the Big Bang happened. The universe is expanding, and it used to be expanding much faster than it is now. And that means that the simple answer isn't good enough. I don't want to get too deeply into the details of the Big Bang, but it boils down to the idea that the universe was once smaller and hotter and has been expanding since the beginning. I made a video about it if you want more. And that expansion is key to understanding what is going on here. We start by imagining what the universe looked like when this microwave background radiation was emitted. It was hot everywhere. No place was special. Well, I guess one was, kind of. And that place is the current location of Earth. But at that moment, it looked like everywhere else. Now, there was a sphere centered around that point and at that time, and that sphere is the origin of the cosmic microwave background arriving at the Earth now. That radiation moved toward the Earth at the speed of light, and it took 13.7 billion years to get here. If we look at a sphere smaller than that special sphere, that light has already passed the Earth, and we can't see it. Light from a bigger sphere isn't here yet, so we don't see it either. When this light was emitted shortly after the Big Bang, this sphere's radius was about 42 million, that's with an M, light years away. Naively, you'd expect that this light would have taken 42 million years to get here, but it took 13.7 billion, and that's with a B, years to travel to Earth. And the reason that it took so long is that space was and is expanding. Now, if you think about that, it means that space between that sphere and the location of the Earth had to be expanding pretty fast. Otherwise, the light would have passed by the Earth long ago. I mean, it was only 42 million light years, and it's been nearly 14 billion years. So that sphere from which the microwaves were originally emitted also grew in size. And, in the simplest calculation, that sphere would now be 41 billion, that's with a B, light years away. However, it turns out that the simplest calculation isn't quite right. You see, about 5 billion years ago, an energy field that we call dark energy became important. Dark energy is a repulsive form of gravity, which means that the expansion of the universe isn't slowing down, it's accelerating. That, of course, that means after 9 billion years of the expansion of space slowing down, it's now speeding up. When you take into account the effect of dark energy, that radius of the sphere from which the microwaves were emitted has grown from 42 million with an M light years to 46 billion with a B light years. And this highlights the confusion that arises from expanding space. We see the light from shortly after the Big Bang. It was emitted a short distance away, and now the location from which it was emitted is now about 1,100 times farther than it was. Further, when we see it as it was then and not as it is now. Indeed, remember that when the light was emitted, the conditions at the location of the sphere were the same as here on Earth. But the conditions here have changed. Instead of a bath of energy, we now have stars and galaxies. That's also true on that sphere. So, if we could somehow see 46 billion light years away, presumably there are also stars and galaxies. But we don't see them there because light from objects that are currently that far away hasn't had time to reach us yet. In fact, and this is a mind blower, we'll never see those stars and galaxies. After all, they are moving away from us very fast and space is still expanding. We saw that the location when the universe was young, but we can't see them now. It gets weirder. Currently, there is a sphere around the Earth with a radius of about 15 billion light years. Objects that are now outside that sphere at this moment will never see as they look now, no matter how long we wait. I'll repeat that so it can sink in. We can currently see objects 46 billion light years away, but we see them as they were in the distant past. And any objects that are currently within 15 billion light years, we will be able to see as they are now, although we'll have to wait a long, long time for that light to get to us. And because of the expansion, it gets worse. It means that we constantly lose stars that we can see. Indeed, we lose about 20,000 stars per second. So there are stars that emitted photons at this moment that we will eventually see, but the photons that they emitted at this slightly later moment that we'll never see. One day, the expansion of the universe will make it so that almost all of the galaxies we see in our telescopes today, which I remind you now we're seeing as they were in the distant past, will slip from our view. We will one day only be able to see galaxies from our local group, meaning the Milky Way, Andromeda, and a few dozen minor galaxies in the vicinity. So that's the answer to the question. Our visible universe has a radius of about 46 billion light years, even though it's only 13.7 billion years old. But we're not seeing that distant point as it is now, but as it was shortly after the universe began. And the ongoing expansion makes things even worse. The bottom line is that if we're ever going to try and explore other galaxies, we better get cracking. Okay, so that one was something of a mind blower, but that's cosmology for you.
I love the dramatic music at the end there, but I thought that was really fascinating. So I included it for you guys to watch. So he does have some very interesting points, especially at the beginning. Those things will possibly be touched on your quiz about the fact that the temperature of the universe is decreasing. It was much smaller and hotter when the Big Bang started, and that it's expanding.
If you like what you heard, please like, subscribe.
Yes, okay. I always end up doing that. Okay, so let's continue onward. So that was a nice little break from my voice. So there are a few pieces of evidence that we have to help us discuss the expansion of the universe here. And so a few of these items here that I've listed are things that help show evidence for the expansion of the universe here. So the first thing on my list here is redshift. So redshift is the shifting of a specific frequency to a lower frequency. So if you're seeing redshift, that's what's happening there. Now we also discussed blue shift. That's the shifting of a frequency, a specific frequency, to a higher frequency. And then we also have Doppler effect. And this is basically the changing of a frequency from what it would be if a star or a galaxy were motionless relative to the observer. So these three things are showing us that there is evidence for expansion of the universe, because we do see redshift. So we do see it going from a frequency to a lower frequency. So we're seeing redshift. We are seeing no blue shift. So we're not seeing a specific frequency going to a higher frequency. And then we are, which it would be moving toward us, right? So if you see here, and then the Doppler effect. So if something is moving toward us, the frequency would be higher, right? So that's our blue shift. But since we see things moving away from us, this would be our red shift here in our Doppler effect image. We would have a low frequency. So in my image here, so let's pretend that this image here is our universe, right? So let's pretend that we are Earth, and he is the little guy on the far left. And so the guy on the far left is Earth, and let's say the ambulance in this example is Andromeda, a galaxy that's most similar to our galaxy. So we know that the universe is expanding outward, and just like the bread and raisin example, those galaxies are moving away from us, right? So we can prove this because we are seeing redshift. happening, which is basically the frequency moving to a lower frequency. And so the little guy on the left here, Earth, that's us, remember, if we have us at a stationary point and then we have the ambulance, which is Andromeda, moving away, we're going to be experiencing a lower frequency, which is our redshift. Now, if we were Earth and we were the guy here right on the far right, and Andromeda was moving towards us, we would be having a higher frequency. And that's not the case, because if we were experiencing a higher frequency, we would be seeing blue shift, and we're not seeing blue shift. So that's just a good example, kind of a visual to kind of show where the evidence is for the expansion of our universe here. Okay, and so when we talk about Doppler effect, that little image is here again. You can see with the ambulance and the frequency, right? So in your quiz, you might get a question asking you to calculate the Doppler effect, or the frequency here. And so when we talk about Doppler effect, it does refer to a few different changes. So there's a few different things we're going to be discussing. So you might need a couple pieces of information if you're going to be solving a Doppler effect question or a frequency question here. So you will need, when we talk about Doppler effect, it refers in changes to things. And these four things include amplitude, speed, wavelength, and frequency. So how tall or short the waves are, the speed of the wave, how long the waves are, and the frequency. And so let's kind of, this is the equation we're going to be using here. F equals parentheses C over C plus Vs parentheses times FO. And so each of these items represent a different thing. So our F in this equation for Doppler effect is our observed frequency. So that is the frequency that we are observing. So say we were standing on a street corner, and that is the frequency we are hearing coming from a point. So if I hear like a tornado siren, what I am hearing is my observed frequency, the frequency that I'm hearing. Now our C in this case is our speed of sound. And for all intensive purposes, it depends on the temperature. So it can range from 340.7 meters per second to 343. So for all intensive purposes, let's use 343 in this particular case. So we would plug in 343 for both of the C's, because that is a constant number. We will always be having a very constant speed of sound in this case. So if you get a question, that is what our C would be. And then we have our Vs. So this is our velocity of our source for our Vs. Now, this does depend if something is moving toward you or away from you. So if I'm sitting here and there's an ambulance moving toward me, it's going to be a negative number. Now, if I'm sitting here and it's moving away from me, it's going to be just a regular positive number. So make sure you remember that if you get a question based on the Doppler effect on your quiz. So that would be typically provided in a question that you would get. And then our FO, this is going to be the emitted frequency of a source. And so that's the actual frequency that a source is emitting. So this would be if we had an ambulance that was, had its siren on, that would be the frequency that the ambulance itself is spitting out into the world. Or a tornado siren, the frequency would be what the actual siren frequency would be emitting. Okay, so just remember this equation. I'm not sure if it is in your book, because when I was flipping through it briefly, I didn't necessarily see this particular calculation. So hopefully you all are watching the lectures, and therefore you'll have this information. Okay. So now let's get into some Big Bang time frames here. So this is a unique little image right above me here. You can see it looks like maybe like a glass or a cup in this particular instance that's kind of getting larger at the top. I guess that's supposed to be the universe expanding outwards and getting longer. But if you look at the very bottom of the cup here in the yellow zone, that is near where the Big Bang actually occurred. It starts as like a point almost in the funnel here. And so let's talk a little bit about time frames. So what's happening at each point right after the Big Bang happened. So we know the Big Bang occurred, but there are a few different eras and phases that have happened right after the Big Bang happened. Okay, so let's look at the first important milestone here. So right at a millionth of a second, which is like kind of the first important thing to look at. So this is basically a microsecond after the Big Bang has occurred. And so right after that happens, there are some things that are being formed. So we have quarks being formed, we have antiquarks, we have electrons and positrons that are forming. And so I have a definition for quarks on the next slide, but basically it's a subatomic particle that has energy. And so this is what eventually will start to form atoms and neutrons and protons and electrons. So, okay, so that's what's happening right at the very, very beginning of the universe. We have all of those weird little quirky quarks being formed. And so right after that happens, right after that microsecond occurs, then we have a microsecond that goes to a fraction of a second. So this is the space between that. So we have a microsecond to a fraction of a second that's occurring, and in this time period, we have neutrons being formed and also protons. So right after those quarks and antiquarks are happening between the first two time periods, a millionth of a second and a microsecond, now we have a microsecond to a fraction of a second, and we get those neutrons and protons being formed. Next up here in this time frame on this cup, and I'm sorry that it's kind of small and it's hard for you to see, so I apologize for that. But we're moving upwards in the formation of the universe here, because at the very top of that cup, that's present day. So in the area here between a fraction of a second and a second, right after the Big Bang occurs, now we have hydrogen and helium nuclei beginning to form. And so we have actual atoms being formed. And so that's what's happening next in the time frame here. And then between 1 and 3 seconds after the Big Bang occurred, we have electron pairs forming, and now they start to begin to orbit the nuclei, or the nucleuses that have been formed. And so I have a couple refreshers here too, coming up in a few slides on what protons, neutrons, and electrons are. So hopefully that's all a refresher for you, and you guys all are aware what those items are, but I've included it in a few slides here. Okay, so that is pretty much what we are talking about in terms of time frames of what's happening right after the Big Bang occurs. But we also have a few different eras that I just want to point out here. So two eras that we have are our radiation era and our matter era. And so the radiation era was a very small point in time. It's the first 1/100th of a second. This is basically energy only, hence radiation era. Very creative on their names. But that is what was happening at the first era that we have here. Now, nowadays we have what we would call our matter era, which is between 1/100th of a second to today. So that's quite a bit of time. And this is when the hydrogen and helium is being formed. So we have actual matter, not just plain old energy. So those are just our two eras that I'd like to point out. Okay, and, ooh, sorry, this got cut off just a tiny bit right there, but so these are just some basic structures of what an atom is. And so you can see, hopefully, I think some of this didn't, oh, there we go. Okay, so we have our atoms here. So we have the main particles that make up an atom are what we would call protons, neutrons, and electrons. So depending on what we have here, we have those particular particles. Now you can see, hopefully, there we go. Okay, so we have our nucleus is typically formed up of protons and neutrons. Now you don't always need a neutron in your nucleus, but you do need protons at the center here. And then you also have electrons, and they are in the shells surrounding the center of the nucleus. And so they're swirling around on the outside of the nucleus. And so our protons here are positively charged particles. Our neutrons have a no net energy charge, and electrons are negatively charged. And so you can see in this atom, this basic structure here, you can see in the nucleus, on the structure on the left only has one proton and one electron circling in its shell here. And then on the atom on the right hand side, you can see that there are several protons and several neutrons in the nucleus, and we have several more electrons circling our nucleus in its varying shells. And if you recall correctly, electrons are stacked accordingly in the outer shells. So there's 2 electrons that fill the first shell, 4 electrons that fill the second shell, and so on and so forth, depending on how many electrons is in a particular element or an atom. Okay, oh, this got kind of cut off. I apologize for that. I was hoping that it wouldn't, but it did just a little bit. Okay, so which element the atom comprises is basically determined by the number of protons in its nucleus. That is what we would call the atomic number. So that is what we see if we have a periodic table of elements. We do see the atomic number there in that element table. And so depending on how many protons you have in the nucleus will determine which element you have. If you have hydrogen or helium or lithium or boron or whatever element you're discussing at that point in time, that's basically they're classified by the number of protons in their nucleus. So on the right hand side here, you can see that this image is actually a carbon atom. So our carbon atom is comprised of 6 protons in the nucleus, 6 neutrons in the nucleus, and 6 electrons in the shells surrounding the nucleus. But the atomic number of carbon would be 6, right? Okay, that was me pretending to let you guys answer. Anyway, we also have on the left here a hydrogen atom. So our hydrogen atom has 1 proton, 0 neutrons, and 1 electron. And so the atomic number of hydrogen would be 1, right? The number of protons in the nucleus, okay? So that determines the element. So it does. You're not really looking at neutrons, you're not really looking at electrons, even though they are important. And we'll talk about why neutrons are important in a second here. But let's move onward. So hopefully that's all review for you. You probably all have taken a more basic science or a chemistry class, at least at this point. Okay, so I talked a little bit about this here. So remember, the nucleus contains neutrons and protons. Electrons are in the outer shells here. Remember, I kind of mentioned this already, but our protons have a positive charge. So pro, positive, pp, that's kind of how I remember it. Neutrons have no net charge, so they're exactly what they sound like. They're neutral. So neutrons, neutral, no net charge. A lot of alliteration happening here. And then also you have electrons. They have a negative charge. So I look at the E and see like a negative sign in the middle there, and that is what helps me remember that, you know, your electron is your negative charge when it comes to when you're talking about an atom here. Okay, and I mentioned quarks before. So quarks, remember, they were present when right after the Big Bang happened, at the very beginning formation of the universe. So these are subatomic particles, and they carry a very fractional electric charge. So they're not really organized, and they're just subatomic particles. And eventually, they do help become your proton, neutrons, electrons, and then eventually atoms after that. So. Okay, so I mentioned that we discussed why neutrons were important. And so the reason that neutrons are important is this word here, which is isotopes. So basically, when you have isotopes, it's varying numbers of neutrons in the nucleus. So atoms of any single element here can possess a number of different neutrons. So you can have carbon with a varying number of neutrons in the nucleus, right? So if you have a carbon atom, remember we had 6 neutrons, 6 protons, and 6 electrons, right? So that's carbon-12. So that's your typical carbon. That's what you would see in the periodic table. Now, if you have an incident where all of a sudden there's 7 neutrons in your nucleus, or 8 neutrons in your nucleus of a carbon atom, and then this is what you would call an isotope, which had that varying numbers of neutrons in that nucleus here. And so isotopes are important because they can be radioactive. So they're basically an unstable form of an element that emits radiation as a nucleus starts to break apart. And so if you have a radioactive isotope, it will eventually decay or break down, and the half-life is the amount of time that you would have to wait for a radioactive isotope to break down 1/2 of the atoms in a sample naturally. And so you have a lot of different elements that are radioactive isotopes that take thousands of years for a half-life to occur. When you're talking about the more radioactive isotopes, if you're talking about like uranium or some other element here that is some sort of radioactive isotope, it can take hundreds and hundreds of years just for it to break down into half of the original sample. And then after that happens, it would take the same amount of time for that half to break down into another half of the sample, all the way until you would have none of that isotope left. And so say your half-life was 100 years for a radioactive isotope. It would take 100 years for the original sample to break into half, and then another 100 years for that sample to break into half of that, and then another 100 years for that sample to break into half of that, and so on and so forth. So right now, I mean, just those 3 half-lives that we have, we're already at 300 years. So it can take quite some time for a radioactive isotope to break down. Okay, so you have already seen this HR diagram before. This is just basically a little bit of review. I just wanted to just really be more concise when I was discussing what the HR diagram had, at least in the 3 stages of a star, at least one that's very similar to our sun here. So you can see the main life stages here in this HR diagram. But I'm just going to highlight them very quickly, so that way it's more of a review for you. But this is, I mean, it's very important, at least for us to know for this chapter or this module. So your first stage is your contraction stage. We talked about this. It's basically born from huge clouds of hydrogen, if you recall. And then the second stage goes into the main sequence stage, which is gravity pulling all of that hydrogen into the center. Pressure is building in the core, the temperature is increasing, and nuclear fusion reactions are happening. which is the hydrogen turning into helium. And so that's what's occurring in the core there in the nuclear fusion reactions. Not to be confused with nuclear fission actions. It's fusion. And then also we have our fuel exhaustion. So this is when the star is running out of the hydrogen fuel to fuel the fusion, or the fusion of hydrogen into helium. And then we have elements through masses of iron that are end products. So we have iron, that would be like the very end stage. And then the last stage depends on how large the star is, or the mass of our star. So in the main sequence, we have in our core here, we have the hydrogen and the helium fusion reactions pushing that energy out. We have gravity pulling the mass in. This is in our main sequence stage here. The steady state of emission of radiation is happening, and then also the length of this stage is depending on the mass of the star. So really the mass is controlling a lot of how long each of these stages are lasting. Now remember, we have our red giant stage. So this is when the hydrogen fuel has been depleted and we're getting less energy out, and the star itself is starting to collapse. But we have a few things that are happening at this stage. We have increased temperature and pressure beginning to fuse beginning to fuse hydrogen in the former shell to helium. So hydrogen to helium. We have a less brilliant red emission, a lot lower temperatures for the large red giants here. They are much larger. Eventually, the sun will enclose Earth's current orbit. And then elements up the mass of iron being produced in the core. And so iron is one of the end elements here. So when a star dies, which is very sad and unfortunate for the star, there are one of three possibilities that are happening after the red giant. So the three possibilities that we have all depend on the mass of the star. So the first option that a star might go is the white dwarf to the black dwarf. And so this is basically for relatively smaller stars like ours. So our sun is a smaller star. So this is likely what would happen to our sun at the very end phase during his death. We would have a white dwarf end up being a black dwarf. The second option, we would have a neutron star being formed, which is for relatively larger stars, and we'd have the carbon being transferred into iron. And then you'd have a nova, which would be a new star here. And then lastly, you would have an option of your star turning into a black hole. These are for the very largest of stars, and this is happening when the neutrons are collapsing. So these are your three options. This is a nice example here of the possible options of what would happen to your star. Hopefully you can see that. I don't know if you can see that well. But those are the three paths that might happen after a star is in its red giant phase. So our star is currently in the main sequence, so it still hopefully has a few more million years of existing. Not that to say that we will all still be around, or at least the human race, but I don't know. We will see what happens. So what are the implications for life when we're talking about all of these stars, or our sun? What happens when we have different size stars? Is life found in other parts of the galaxy? So what happens if you have a very large star? So if your star is too large of a star, what is happening here is it's burning out too quickly for intelligent life to evolve. Now, remember, it takes millions of years for us to evolve, or for a species to evolve. And so if you have a very large star, that doesn't give you enough time for any sort of intelligent life to form before it burns out. So then that would be no use. Now, what if we have too small of a star? So if the star is too small, it's going to burn very slowly, and it's going to have low amounts of life, which wouldn't necessarily be great for low amounts of light, which wouldn't necessarily be great for life on a planet that might be close to the star. And so maybe you're not, if a star is too small, maybe you're not getting enough light for any sort of plants or any sort of plant-like type organisms to develop and evolve. But we have life in our solar system, and that's because we had a star of intermediate mass. So it's kind of like Goldilocks and the Three Bears, or maybe that's a terrible example because I think that they picked the small star. But anyway, you want it just right. You don't want it too large, you don't want it too small, you want it right in the middle. So we had an intermediate sized star, and this eventually gave us several billion years of regular, steady energy output in order to have an array of planets such as ours in its solar system, and for life and conditions to be just perfect for us to be formed and get to the point where we're at in today's world. And so this is my last slide for this particular presentation for this last part of the module. So how old is Earth? Remember, we talked about this in past modules. So we think that Earth is approximately 4.6 billion years old. And we're confident in this for two reasons. The first one, if you remember from a few modules ago, we are confident because of geological records, and also because of uniformitarianism, which is if the conditions stayed steady and continued to happen on Earth's surface over the course of time, it shows us that there are varying occurrences that happen in the geologic record. So, all right, so that's all I have for the presentation for today. That concludes our Module 10 on the universe. Next week is probably going to be a little crazy. We're going to try to squeeze 2 modules into next week. I'll try not to make the presentations too long, but since we took an extra week of spring break, it's caused a little bit of a hiccup in my lesson plan here. So we'll try to make do with what we have, and hopefully it'll turn out for the best. So I look forward to all of your presentations. I'm really excited to see and hear from you all. I just miss people, and hopefully your quarantine is going well. So, all right, good luck on your presentations, and you'll be hearing from me soon.